Hi. So when you look at section 3.3, it makes absolutely no sense. So you're looking at this thing, you're not understanding the thing they're talking about because they're trying to make it sound so difficult. What you're trying to do is you're experiencing exponential growth. That means we're saying that something is going to grow at the same rate over a long period of time. It's an estimate of how fast something's going to grow or occur. And basically, we're going to just use two formulas. P sub t, this means over a period of time, this is the amount that you're going to get back if it's money, or this is the amount it's going to, if it's population, this is how much the population is going to be over a period of time, maybe 1 year, 2 years, 20 years, whatever. T stands for time. This is the amount P sub 0 is the initial amount that you started out with. It could be the initial population, it could be the initial amount of money you invested. It's the initial amount that you started with. E is your exponential growth. This is your growth, and it's growing exponentially as a representative of E. K is the actual growth rate, is the constant rate that it's growing at. It could be a percent if it's money, or it could be an actual growth rate that's going on. And then T is the amount of time that it's going to take. How long do you want this to grow? So if so, let's write down some of these things. This is the final amount that you're going to have, the finale, final amount. This is the initial amount, the initial population, we call it, and this is the final population. It could be money, it could be anything. E is a constant, right? It's always in the formula. K is also a constant. It's a constant rate, constant rate. And rate, remember, could be interest rate or it could be just a growth rate. It's a rate at which things are growing. And T is the time it takes to reach that. So let's start out with a pretty easy problem that may sound difficult in the book, but we'll take a look at it. Number 7. This is on page 347. Okay, it says, it has this patent thing, but the main thing is it says the people applying for patents it drew dramatically in the recent years. About 4.6% are applying for patents, 4.6% per year. People want to buy patents. So we're going to try to find an equation. And this was the initial year was 1980. They're basing this on what happened in 1980. And since then, they've noticed that the growth rate has been about 4%, 4.6% per year. So the first question is here, it says, find the function that satisfies this equation. Assume that T0 was 1980. So we're going to say the population in year 0, which is 1980. But we're going to just put a 0 here for the first to start off with, is equal to the initial population. We don't know what that is. We're writing a general formula. We don't know what that is. That's the initial population. We didn't know how many patents were back then. Okay, E. But the constant rate of growth is 4.6%, but we need that as a decimal, not as a percent. So we're going to have to write this as 0.046. This is very important because if you don't write it that way, you have your decimal in the wrong location. And then T is going to be how many years it's going to take to grow to that. So that's our initial formula. This is our starting formula. And that's what they wanted right here. That was the question they wanted. They didn't really say it in so many words, but that's what they wanted was this starting formula. And they did say that 112,000 patents were received that year. So in that initial year, I guess we'll change this a little bit. We do know that there were 112,000 patents. So we're going to write that as P. That's our initial amount. So this actually was the formula they wanted. This is our general formula. Now, the next thing we're going to do is estimate the number of patents in 2020. So what we're going to take is 2020, going to subtract the 1980, that's 40. So we want to know how much growth is there going to be 40 years from now. That's what we're trying to find. 40 years from now, from this initial start, is what has happened. So this is going to be 112,000 e to the 0.046, and the time is going to be this 40 right here again, 40. So 40 years later. So all we have to do is just put this in our calculator. Let's start out here. Let's clear this thing out. Can you see it okay? I can't. Okay, it's covering my problem here. I got to see the problem. Okay, 112,000,000. Too many places. I don't know. Let's clear this over. Start over. 112,000. Okay. E, second ln. Parentheses, that's exactly what we want. 0.046 times 40. That's all in the exponent. And then just hit equals. Now I got a little smudge on my calculator. It almost looks like a decimal point there. It's not. So now, 20 years later, if this growth rate continued, 4.6 per year, we get 752. I'm going to put in my decimal point in a minute. Point something or other. We just round off to the whole number. So it should be about 705,212 patents in 2020. That's how many going to be. It's growing at that rate. So about 700,000 patents as compared to 112,000 in 1980. In 2020, that's how many patents were applied for. Let's put patents. That's what this is asking. In 2020, there's going to be about 705,000 patents. Okay, the last thing is estimate the doubling formula. The doubling formula has another formula. This is our initial, this is exponential growth rate. But I'm going to put it up here, doubling formula. And it's very simple. We could do a whole bunch of work here, but this is kind of a shortcut. It's the natural log of 2, ln2, divided by whatever the growth rate is, k, divided by the growth rate, k. So in this problem, it's going to be ln2 divided by k. It's going to be ln2, k is what? 0.046. This is our k right here. So we want to divide that by 0.046. And that would tell you how much time it takes for whatever it is to double. In this case, patents. The number of patents that will double. Let's go second, not second ln. You just want ln2 finish your parentheses, divided by 0.046. So every 15 years, approximately, every 15 years, the number of patents will double. From 1980 on, every 15 years, the patents doubled. See, we can use this for this outbreak. How fast is it doubling? How many, if we have 100 patients getting sick, how long is it going to take before 200 get sick? We can figure doubling time. Okay. So that's what they were talking about on that problem. Let's try another one. Maybe I'll make it a little bit bigger so you can see a little bit better. Let's try this one with a little bit darker. And then I'm going to go back and do a problem out of the assignment, but out of the lesson. Number 9. It says, suppose the initial investment is in this multi-branch fund is compounded continuously. That's where the E comes in. That's compounded continuously at 5.9% per year. 5.9% per year. And it's continuous, which means it's going to involve E. What is the balance? That is, the balance grows at such and such a rate. We're not going to get into that. Confusing as heck. Okay, so it says, let's go to the next page, A. It says, find the function that satisfies the equation. Write it in terms of the initial investment and 0.059. So investment over time will equal the initial investment times E to the 0.059. See, I've got to change that to a decimal. And then this is going to be times the number of years, T. So that's our initial formula. That's our starting formula right there. Now, B, it says, suppose that $1,000 is invested. Okay, I'll fill that in. What's the balance after 1 year? The balance after 1 year is going to equal 1,000 times E to the 0.059 for 1 year times 1. And that's our formula. So we're just going to put it in. It's going to be 1,000. Second ln to get E. Yeah, let's see if I can put this someplace where you can kind of see it. You can see it pretty good there, huh? Second ln, and then 0.059 times 1. Well, I'll put it in the times 1. It's not going to change anything. Bingo. So this is how much money you should have coming back after the first year. $1,060, and we're rounded up 78 cents. Okay, that's how much you're going to have coming back after the first year. Now, after the second year, let's see how much money you have coming. You put in $1,000, E 0.059. Now we're going to multiply by 2, second year equals. And we're going to just go up here to my calculator, slide this over, and let's change this 1 to a 2 equals. So now I should have $1,125.24 approximately coming back to me. Based on an initial, and we could do this for 30 years. Let's say you wanted to find out how much you got coming back after 30 years. This would be 1,000 E. it's continually going to pay the same interest. And this interest is compounded every second. That's what's going on here. Times, I just put a little time sign 30, and let's see what happens. Okay, so again, we'll go up here, slide over, and we can just change this 2 to a 30. And let's put a parentheses to end it. So you would have, I thought it would be more than this, $5,870.85 coming back to you after 30 years. Let's find the doubling time. It didn't ask for the doubling time, but we can find the doubling time. How? ln2 divided by the constant, 0.059. Just that easy. And this will tell you how much time it takes for it to double. So let's try that. Clear this out. ln2 parentheses divided by 0.059. It takes about 11 years, 11.7 years, almost 12 years for your investment to double. That's why it took so long here. The higher the rate of interest, quicker time it's going to take to double. So that's what doubling time means. Okay, let's look at number 15. It says oil demand. The growth rate demand for oil in the United States is about 10% per year. When will the demand be double that of 2006? 2006, when will that be? Well, let's find out. ln2 divided by the rate. The rate was 10% per year. 10%, but we want that as a decimal. So add a decimal, move your decimal point over 0.10. So ln2 divided by 0.10. So every about 6.93 years it's going to take to double. So 7 years later, let's say, where was that? 2007, 2006, 7 years later, 2013, it doubled. 7 years later, 2020, the demand is going to double again, just roughly 7 years. So we can kind of tell if the demand was, didn't say how much, demand was a million. Then in 2013, it'd be 2 million. And then that's going to double 4 million. See, based on that rate. Now, that rate can go up or down. You know, right now it's 6.93 and evaluated maybe 7 years later when they evaluated, it's not growing that fast or it's growing faster. So this is an estimate, always remember. The growth rate right here was 10%. I'm sorry. Growth rate was 10%, but it might go down. It might only be 5% growth rate. So we don't know. Okay, let's try some more problems here. Let me flip this over. So let's try this one problem in the book. Looks interesting about the baseball card or something like this. And now let's see if it makes sense. Let's take a look at example 7 here. It says this card in 1939, this comic book originally cost 10 cents. In year 0, it was 10 cents. And that was year 0 was 1939. You paid 10 cents for this comic book. And then in 2010, so 2010, take away 1939 is 71 years later. 71 years later, this comic book sold for $1,075,000. That's what they're saying here, that it grew that exponentially that year. So they want us to write an initial, what they're saying, find the function that satisfies this equation. Okay, so they want the initial function, p sub t, that's going to be your final result, is equal to the initial amount, p sub 0. So you don't want to put p-o, it's p sub 0 times e to the k times t. That's our initial formula, but we're going to change it a little bit. Do we know the growth rate? No, we don't know. We don't know the growth rate. We don't know a lot of stuff like that. That's all we know. We know that the initial amount was 10 cents. That's about all we know. And you don't want to write 10 cents this way. You want to write it as 0.10. Okay, so that's all we got. Okay, so number 2 says estimate the value of the book in 2020. 2020. Well, that'd be 10 years later, so that'd be 81 years from now. It'll be 0.10. That's not going to change. E to the constant. Well, we don't know the growth rate, do we? We don't know how fast this is growing. So this is going to be a little bit difficult to do because we don't know that rate, but we do know that it's going to be 81 years later. So how in the heck are we going to do this? How are we going to calculate this? Well, let's see. We got to find this growth rate. We got to find this rate of growth. This is the formula we're going to use for 20 years later, but let's use the amount now. 71 years later, it was 1,075,000. And that was equal to the initial rate that it started out at, 0.10 times E. And we don't know the constant, as we were trying to find the growth rate. But we knew that this was 71 years later. So we do have a formula that we can find K. K is the rate of growth. We don't need to find E because E is a constant. So first thing I'm going to do is divide by 0.10. There's a couple of different ways you can do this. So if I take that 1,075,000 and divide it by 0.1, I get even a bigger number. I get 10,750,000 equals E, because that's 71K. Now, you can do this 2 different ways, but the book does this, and this is pretty good. If I take the natural log of E, let's take the natural log of E. This would be ln, the natural log of second ln E. Let's raise it to the 1 power just to make it an E. The natural log of E is equal to 1. Okay, so I'm going to take the natural log of both sides. I have to do this in order to get rid of E. And also it involves doing something else. There's a certain property of natural logs and logs that say it's called the power theorem. And when we take the natural log of E, we can move this power in front. We can change that to a multiplication problem. They don't really show this too well in the book. So that becomes 71K ln E. But we know ln E, the natural log of E, is 1. So this is the natural log of 10,700, 10 million, such and such, equals 71K. So if I take that and divide this by 71, I'm going to find my growth rate. And that's what I'm trying to find, the rate at which it's growing, this constant rate every second of every minute. So it's going to be ln 10,750,000 divided by, and I want to close off this parentheses. Again, you can't see that too well. I want to close off the parentheses. I originally put a ln in front of there. And I want to divide that by 71. I'll show you in a minute. And this comes out to 0.228. So this comic book was growing at 22.8% per year. It was increasing in value. First year it didn't increase a whole lot, but because it was only 10 cents. Oh, I erased it out. Let's see if I can get it back. Okay, you can see I put an ln. You can't see. I put an ln and then I slid across here and then divided by 71. So that's the rate at which it's grown, but we do want it as a decimal, so that's good. So now I'm going to go back to this equation right here, because the question was estimate the value in 2020. So we needed this growth rate. So I'll put it down here. I think we got just barely enough room on the paper. 81 years later, what is this going to be worth in 2020? This is the value of the comic book. It's going to be 0.10 e to the 0.228 times 81. Okay, so let's put that in our calculator. Move that out of the way so you don't have to bother with it. It's 0.10 e second ln raised to the 0.228 times 81 parentheses. This comic book is now worth whatever that big number is. Let's see, let's write it down. 456.82. The estimated value of this comic book in 2020 would be $10,480,566 and some change. Is that what they came up with? Pretty close, yes. So that's pretty much the value of this comic book in 2020. Now, what's the next question? What is the doubling time? Well, the doubling time is really easy. That's just ln2 divided by k. You see why we had to find this k? 0.228. So that's easy to do. We just take over here, ln2 divide by, oops, here, let's finish off that parentheses because it could throw off stuff. Divide by 0.228. 3 years. It takes about 3 years for this to double. Is that what they came up with? 3.04. So every 3 years, the price doubled. So in 1938, if you bought this 3 years later in 1941, this comic book was worth 20 cents. Not a whole lot. But in 1980, 2020, we see that all of a sudden it's doubled. So this amount keeps doubling. It's pretty amazing. Reminds me of a problem, and I think that's all we have to do. Let's see if there's one more problem. What will be the year in which the comic book will be worth $30 million? Oh, when will it be worth $30 million? Well, the year. All right, this one's going to be a little complicated, huh? We want to be $30 million. We know the final outcome. And we know the initial amount, and we know E, and we know 0.228, but we don't know the number of years. We're trying to find T. So it's kind of like what we did before. We got to divide this by 0.10. So that's going to increase this even larger. It's going to be 300 million equals E to the 0.228T. Okay, then we're going to take the ln of both sides. And I like to write this step down. This would be 0.228T ln E. But we know ln E is going to become 1. See, we're moving this in front. And now we can divide this by 0.228, and that should give us our answer, 0.228. And this should give us the time. Then we're add that to show you what we do with it. So this is 300 million, 0, 0, 0, 0, 0, 0, divide by 1. I need the ln of that. Let's erase it. ln 300, 000, 000, 000. I guess that's it. I hope. Boy, I'm not doing so good here. ln. You probably already got it figured out. 1, 2, 3. 1, 2, 3. Yeah, I did have a percent. ln divided by 0.228. 85.6. So 85.6 years. What are we trying to find? He rounded off to 86 years. Okay. It's going to take. So in 1939, it was worth 10 cents. And we want to get it up to 30 million. So we're going to add 86 years to this, 15, 83 is 11, 12. In the year 2025, this comic book, 5 years from now, this comic book should be worth $30 million if you continue doing this. $30 million. If you have $30 million laying around, you can probably purchase this comic book. Well, that's an estimate, and you never know. The value could go down. I happen to have this comic book, but unfortunately it's a reprint and it's not the original. But still kind of interesting to have the reprint. One year they were printing out reprints and I picked it up for 10 cents. So that gives you an idea. I want to show you one other quick problem. I kind of ran out of time, but I want to show you a little problem. There was a gentleman that he was working for this company, and the company needed his services very badly, and they said he would have to work 30 days straight without a day off, without any time off. And they said, I'll tell you what we do. It's a lot of days you're going to be working. For those 30 days, we'll give you $100,000. 30 days, $100,000, no time off. You're just working straight 30 days, but in 30 days you get 100,000. And the guy said, well, can I counter your offer? I said, sure. What would you like? You can try. I don't know if we can go much over that. He said, I'd like to just get paid a penny a day. And each day it'd double. I guess a penny a day. And and then each day it would double. Let me show you. So the first day I get a penny, day 1. And day 2, I get 2 cents. Day 3, you double that. I get 4 cents. And in day 4, I get 8 cents. I said, are you sure? I mean, 8 cents. Okay, he said, we're doing. So the first week goes by. They're going to pay this guy um, every 7 days, and then the final week they're paying him, the extra days. So let's just see what happens in the first week. 6 days, 32 cents. 7 days, 64 cents. Okay, so this is kind of a doubling problem. And isn't that what we're doing? ln2 divided by something. We're doing kind of a doubling. How often does it take this to double? So let's see what happened at the end of this week. He had 64 cents, which, well, let's just add it all up. Let's see how much money he has coming. 0.01 plus 0.02 plus 0.04 plus 0.08 plus 0.16. You might, when you're doing this on your calculator only takes so many digits, so you may have to add as you go. 0.64. Like at the end of this week, he got $1.27 coming to him. So the guy says, I really feel like I'm robbing you. I mean, you would have had, let's say, 4 into 100,000, you would have had close to $25,000 coming to you. And instead, you're getting $1.27. Okay, so that's fine with me. Fine with me. So if you want to continue this down, see what the 30th day turns in. Is it bigger than 100,000? And then find out what the total is for the month, for the 30 days. This would be just the 30th day. And then find out what the total would be for the month. I'll give you a little hint on the total. If I multiply this number by 2, that's $1.28. And if I subtract 1 from that, 1 penny, 0.01 from that, you see I get $1.27. It's 1 less than that. So, I mean, maybe that'll give you a little hint on the total. But anyhow, try that for 30 days. You can mess around with it. And maybe you come up with a little formula for finding that amount. It's not so easy to come up with the formulas, so don't worry about that. But just see if he makes more than 100,000. Was this guy an idiot or what? And then on the next video, I'll tell you what the answer should be. All right. Well, just a little fun problem. And it kind of deals with doubling and stuff like that. So don't get confused by this book. It's basically just a simple formula on this thing. The formulas, by the way, are on page 347, but they're a little hard to find. Here's your basic formula. P sub t equals P sub 0. Initial amount e to the k times t. And then the doubling time is ln2 divided by k. Those are the only two formulas you need for this section. All right.